So last time we talked about the energy-based approach to supervised learning, and this time we're going to talk about the energy-based approach to unsupervised learning. And then in subsequent weeks we'll talk about energy-based approach to structural prediction, but that's not coming for a while. So next week is spring break, just in case you forgot. And the week after that, there's going to be a guest lecture by Jason Weston from who's now at Facebook AI Research. He's in my group actually at Facebook. He just joined Facebook from Google. And he's going to talk about embedding methods. So how to train deep learning systems not to classify or predict, but to kind of find vector representations in which distances make sense. And I might talk a little bit about this at the end of this if I get some time. But if not, he'll introduce all the necessary concepts. Or maybe I'll do a little bit of this in the lab Wednesday. We'll see. Okay, but for now we're going to talk about unsupervised learning so that we can build on the stuff that I talked about last week. Okay, so what is unsupervised learning? So this is a sort of rather kind of key concept in this class, something you probably wouldn't hear anyplace else. And it's been the topic of a lot of active research in deep learning, how to do unsupervised learning properly. And I have to make a disclaimer right away, which is that despite the enormous amount of work that's been on unsupervised learning within the deep learning literature, nobody believes that we have the ultimate answer to how to do unsupervised learning properly. So a lot of the stuff I'm going to tell you about works, but I mean most of it works. But it's not like it's the ultimate answer. There's probably better things that we can do in the future to do unsupervised learning. But at least, today's lecture is going to be about the basic principles with which to think about unsupervised learning. Okay, so what is unsupervised learning? So I kind of alluded to the fact last week that there was really not that much difference between supervised and unsupervised learning. If you think about all the variables that come into an energy function, okay, if you think about energy-based models, in the case of supervised learning, there are variables that we know will always be observed. We call them the inputs. And there are other variables that we know we always need to predict. And we're given the value only on the training set, but we're not given the value whenever the system needs to be used. And there is a clear separation between those two sets of variables. You could think of unsupervised learning as a similar situation, but you don't know in advance which variable you need to predict from which other variable. In other words, there are dependencies between variables, and all of these variables could either be input or output. Some of them you will observe, some of them you will not observe, and you will be asked to predict the ones you did not observe from the one you observed. Okay? So if you have a set of data points like this, so again, that relies on the idea that there is kind of a manifold. It's the manifold hypothesis that natural data lies in a low-dimensional manifold in the ambient space. And so if I give you those data points, there's an obvious dependency between y1 and y2. If you know y1, you can predict the value of y2 to within a reasonably good accuracy. If I give the value of y2, you at least have, for some of the values of y2, you have two possible values for y1, or two possible ranges of values. So it's not a direct answer, but you can identify the dependency, right? And so if you had a machine that could tell you, given y1, give me the value of y2, or given y2, give me the possible values of y1, you would have captured the dependency between those two variables, and you would know pretty much if the point that is being given to you lies on the manifold of high data density or not. Okay? Levin, would you mind closing the door, please, because we're hearing the vacuum cleaner. Thank you. Thanks. Okay, so in reality, things might be a lot more complicated than this. You could have, multiple disconnected surfaces. You could have very fuzzy densities, things like that. Okay, so the natural way to think about this, and the way a lot of people working on unsupervised learning have been thinking about this, is think of this as probabilistic density estimation. So think of this as points that are drawn from a distribution, and what you're trying to do is figure out the density of that distribution from a finite number of samples. This is probably one of the most complex problems there is from the theoretical point of view in terms of building a model, because here it's only a two-dimensional problem, but very often the input comes to you is very high-dimensional. Imagine an image, for example, a few million dimensions. So capturing the dependencies between a few million variables is not easy at all. In other words, it would be like, here's a piece of the image, figure out the other piece of the image you don't see, for example. Or here's a noisy image, find a clean image that essentially removes the noise, okay, makes it natural. So indeed, let's take this example of image denoising. So let's imagine that these points are the set of natural images that we've observed in the world, okay? These are the set of 2-pixel images in that case, but let's imagine is 2 million pixels, okay? So if I give you a data point here outside of the high data density region, and what I tell you is that this image is somehow corrupted, and I ask you to uncorrupt it, then one thing you can do is try to find a point on the manifold that's closest to that image in some distance metric. Okay? And you'll probably find some point here, which you could say is a sort of a denoised version of, or cleaned up or restored version of that image, because it belongs to the manifold of nice-looking images that you've collected. All right? Similarly, if I tell you I only give you 1 pixel value and I ask you to predict the second pixel, then you can pretty much fill in the blank. Okay, that's called image in-painting. So there's a piece of the image and you're asked to reconstruct the other piece of the image. So if you have a good model of the image, if you have a good idea of where the manifold is in the high-dimensional space of natural images, then that's fairly easy to do. So what we need, so again, the natural instinct for a lot of people in machine learning is to say, well, it's just a density estimation problem. We just need to estimate the density of this data. But in fact, this might be an overkill. So we don't actually need to get probabilities out of the system. What we need to have, again, is, the same argument as the energy-based model argument I talked about last week, is that we need a contrast function that tells us how far away we are from the manifold of high data density, and in which direction we should go to get towards that manifold. Okay, so if we have a function that is essentially takes low values on the manifold and takes higher value outside of the manifold, then we can use that function to do the restoration problem I was telling you about. We kind of follow the gradient, for example, to find the closest point on the manifold, or we could look for a value of the other pixel if we know one that minimizes the energy. So that's the idea of a contrast function. In fact, the pictures I'm going to use to illustrate this are the same that I use for supervised learning. So in the case of supervised learning, one variable was supposed to be observed, and the other one was the one that was supposed to be predicted. In this case here, we don't observe. We don't know in advance which one will be observed, which one will be predicted. That's the only difference between supervised and unsupervised learning. Okay. In fact, in terms of formulas, all the formulas that we wrote for supervised learning, all of which have an x, the observed variable, and a y, the variable to be predicted, you can just get rid of the x, and you get the formulas for unsupervised learning. Okay, so the math is the same. In practice, it's different. You'll see in a moment why. Okay, so this is the slide, same as last week, that shows why doing density estimation might be an overkill. It's because you don't actually need this contrast function to be a probability or a log probability, a negative log probability in this case. You just need it to be low on the data and high everywhere else. Okay? And making it an estimate of a distribution is just one particular way of doing this. So in this example here, we have two contrast functions, two energy functions that capture the dependency between the two variables y1 and y2, and they're very different from each other, but they both do the job. Okay? One of them could be seen as a conditional Gaussian model of y2 given y1. The other one, because it's a quadratic function, the other one is not a probability. So as I pointed out last week, you cannot always, but you can sometimes transform energy functions into probabilities using the Gibbs distribution. It's not the only way to do it. It's just it comes from a maximum entropy argument, but it's kind of a convenient way. And the other ways to do it are more or less equivalent to this, up to a redefinition of energy. So take the exponential minus beta the energy, normalized by the integral of that over the whole domain, and what you get is a normalized probability distribution over y, density in the case, it's density if y is continuous. Or vice versa, if you want to think in terms of probability, then the energy could be thought of as the minus log probability, but it's up to a constant which determines the normalization of the distribution. Okay, so here I cheated. Here I just flipped the graph. Really, this should be log probability here. All right, so now we hit the main problem, and again we talked about this last time, which is it's easy to make the energy function low on the data point. What's difficult is how to make it high outside of the manifold of high data density. Okay. And the reason is that the space might be high dimensional, and so there is a bunch of tricks that people have used over the years to ensure that, or to kind of make sure that the energy outside of the manifold of high data density is higher than on the manifold of high data density. So how do we make the energy low on the data point? It's very easy. We have a parameterized energy function, and it's a function of the data point. So yeah, we have forget about the fact that we have probabilities here. Where am I? Here. So we have an energy function parameterized by parameters here. If we want to make this energy low on a particular data point, yi, it's very easy. We compute the derivative of this e with respect to the parameters for the data point, and we do a step in negative gradient, right? So we tweak the w so that e goes down for this particular y. That's very easy. Just gradient descent, right? But now, how do we make it high outside the manifold of data? And that's the tough part. So, we can use various tricks. They are very similar to the ones I talked about last week. The first trick is we make the energy function rigid in such a way that only a given number, amount of volume of stuff can take your energy. And then we don't need to push up on the energy of things outside the data manifold, because if we make the energy of the data manifold low, the other stuff will be high as a consequence, just because the volume of things that can take your energy is limited. Or what we can do is we can design schemes that not only push down on the data beads, on the data points, but also push up on other points outside of the manifold of data. And in fact, there's lots of different tricks to do this. I actually have a list of 7. Whenever I show this slide in tutorials or conferences, people take pictures of the slide because they don't find it there. Yeah, you're welcome to take a picture. It will be on the website eventually. But because it's really expressed in this way, there's a lot of methods that people have developed over the years that actually, when you think about them, are different ways of pushing up the energies of stuff outside the manifold of data, but they're never formulated in those terms. And so it's kind of nice to see all of those methods in one slide in sort of a simple explanation. Sometimes they have cryptic names that are it's very difficult to understand what they actually do. Okay, so the first technique, and we'll talk about this at length, is you build a machine in such a way that the volume of low energy stuff is constant. Okay, so that the machine has a certain amount of things it can move around that will take low energy, that will, dips. It's got a finite number of holes, if you want. Okay, holes in the energy, and it can place those holes wherever it wants, but it's got a finite number of holes. So the result is that it can't give low energy to everything. It's got to place the dips at around the data points. or it's got an infinite number of dips, or infinite, or low-dimensional dips, but they have low dimension, and so they can't cover the entire space. So there are classical techniques in unsupervised learning like PCA, k-means, gas and mixture model, and square RCA are in that category. Okay, so I'm sure all of you here have heard of PCA and k-means. Anyone who hasn't heard of PCA or k-means? Okay, don't be shy. All right. And gas and mixture models. Has everyone heard about gas and mixture models? Okay. No? Yes? And so those are methods that really limit the volume of stuff that can take low energy. And I'll show you some visualization of in fact, I'll show them to you right now. Okay, so let's think about PCA. So the best way to define the energy function in PCA is to define it as the reconstruction energy of any data point. Okay? So the reconstruction energy of a data point for PCA is you take a point, you project it on the principal subspace, okay, through the W projection matrix, and then you multiply by W transpose to project back into the original space, and that's the reconstruction in the original space. Okay, now you take the squared distance between the original Y and its projected and reconstructed version, and that's the energy function for PCA. So it's the formula up there. This thing here. Okay, take Y, project it on the principal subspace, project it back on the original space, and then compute the square difference between the original data point and its projection reconstructed, and that's the energy. Okay, so any point in there, so if you take a point, any point, let's say a point here, and this is the principal subspace. Okay, this principal subspace has been found as the subspace that minimizes the square distance between any point on the data set and that subspace. Okay, so if you take a point on that data set, you project it on this principal subspace, so it's this line in this case. Okay, so in general, this could be a subspace of higher dimension than just one. Here, it's in the whole space in 2 dimensions, so projection is 1-dimensional. Okay, and that distance, the square distance between the original point and its projection, that's the energy. Okay, so the energy function grows quadratically as you move away from the principal subspace on which points are projected, right? And so this particular one, so if I train with points that are sampled from this spiral here, I get this approximation of the spiral, a straight line approximation of the spiral. You can think of it as a fit, which minimizes the average square distance between any point on the spiral and this line. And notice that the volume of stuff that can take low energy here is a line. Okay, it's limited. So if I keep k dimensions for my principal subspace, then it's going to be a subspace of dimension k, and so the volume will be limited by the fact that the dimension of the linear subspace on which I project is not the entire space. Okay, so stuff outside of this will have higher energy than stuff inside. All right, so that's the kind of energy view of PCA. And you can think of PCA as essentially minimizing, when you train PCA, it actually minimizes this energy function, okay, with respect to the W's. So it finds the W on the sphere such that this squared reconstruction is minimized. It also finds a particular rotation of the W in such a way that they correspond to eigenvectors of the covariance matrix, but that's kind of a side effect. You don't actually have to do this for PCA to work. K-means is very similar. So here, the energy function for K-means is something funny. It's not just a direct function. It's defined by a minimization. So it's the minimum of some function with respect to a hidden latent variable z in that case. And that latent variable indicates which of the prototype is being chosen for any particular data point. Okay, so the energy function here says it's going to be the square reconstruction error between the data point y and a particular prototype, which is one particular column of W. Okay, so here W is a matrix, and a particular W is WI, W index I here. It's a column. I will have to transpose it here to make it, well, actually, no, I don't need to. It's just a column. And then I multiply it by a scalar Zi, which is the ith component of Z. And I constrain only one of the Zi's to be 1 and all the other ones to be 0. So Zi, so the minimization takes place over the set of 1 of n codes, where Z is vectors with all 0 except for a 1 at one location. Okay? So that component, that non-zero component, will select a particular column of the W matrix, and that's going to be the ith prototype, or the kth prototype. Okay, so what does it look like? All right, so if I give you a Y, you have to do this minimization with respect to Z to find the closest prototype. That's basically equivalent to finding the closest prototype. And then the energy function is the squared distance between the data point, and the prototype that's closest to it. Okay, so I did k-means here with 20 prototypes, and what you see here is you see kind of, I don't see from where I am, but I'm sure you see from where you are. Those 20 prototypes end up being kind of equally spaced around this spiral. And the overall energy function is the min of a whole bunch of quadratic balls, paraboloids. Okay? So if there is one particular prototype, let's say this one here, there's a dip here in the energy function. You can tell because it's kind of dark. If I move in any direction, the energy function goes quadratically. It goes with the square distance of the point to the center of the prototype. Okay, the minimum of the dip. And then if I move a little too far, then I fall into the territory of the next prototype, and then it's another quadratic ball. And the overall energy function is the min of a bunch of quadratic balls. So there are ridges around each of between each ball there is kind of a sharp ridge, which is, you can go one way or the other. There's another ridge here. That's actually a sharp ridge right here. Okay? So if I'm on the fence here, just on one side I'll fall into one of those prototypes, on the other side I'll fall into that prototype. Okay, so it's a very rugged energy function with sharp cusps. So this looks great. This looks like k-means is much better than PCA, right? Except it doesn't work in high dimension. Because in high dimension, if you want to cover a high dimensional manifold like this with prototypes, you're going to need lots and lots and lots of prototypes, and that's going to become very inefficient. So k-means gets killed by the curse of dimensionality. Okay, so this was technique number 1. Build a machine so that the volume of low energy stuff is constant or is limited. And I'm going to talk about gas and mixture models in square RCA just now. Okay, technique number 2. Push down on the energy of data point and push up everywhere else. So, yes?
You said k-means is valid high dimensions, but on m's, k-means plus SVMs works well, right? 56 dimensions. Do you think that that's much for that context?
MNIST is higher than 256. It's more like 784 or 10. Okay. No, it's 28 by 28. Or 20 by 20 if you center them by bounding box, so it's more like 400. Well, so you mean you train prototypes with k-means, and then you stick a classifier on top of the sparse vector produced by k-means, right? Yeah. Okay, so this only works actually if you use what's called soft k-means, where the vector you put out is not just a whole bunch of 0 and 1, 1, but is kind of soft response. So it's closer to GMMs actually. It works okay. It doesn't work great. It works okay.
Okay.
It doesn't beat any record or anything.
No, but just because it's high dimension and it works well, so...
That's not that high dimension, actually.
Okay.
Yes.
I think maintaining is like fast systems, so that means that we only care about the center of the clusters to match to the load balancing.
Well, okay, there is no notion of cluster here, right? There's no cluster in this data set. It's a continuous line.
But isn't it supposed to be clusters?
Well, so if there are clusters, you would hope k-mean will find the clusters. But even if there is no clusters, it will find, it will put the prototypes around the region of high data density. So that's what's happening here. The points are not, there's no cluster in this data set, but the prototypes end up being all around, equally spaced in that line. Okay, so it's true that k-means is generally used for clustering. It was invented for that, but you can use it for modeling any kind of manifold. So yeah, I mean, it will work better. If your data happens to be clustered, then it will work better, obviously. All right, so option number 2 is push down the energy of data point and push up everywhere else. And to some extent, probabilistic methods, such as maximum likelihood, do that. So let me show you how that works. So here we have a probability distribution produced by the model, P of y given W, where W is the parameters of the model. And it's parameterized as, again, a Gibbs distribution from the energy function. So e to the minus beta, the energy for that particular data point, divided by the integral. Okay, so it's a normalized distribution. If y is discrete, the integral becomes a discrete sum. And what you want is that for every data point in your training set, you would like to make the probability of that data point high. Okay? And the best way to do this is you either make the numerator high or you make the denominator small. Okay, so you have two ways to make the probability of a particular point high. You can either make the energy of that point as low as possible, or you can make the energy of everything else as high as you can. And the probability, the Gibbs distribution only cares about differences of energy. If I add a constant to my energy function, the probability distribution doesn't change. Okay? So if I transform my energy function here in this formula by adding a constant to it, it will appear at the bottom and the top. It will appear as a, because it's in an exponential, it will appear as a multiplicative factor when I get it out of the exponential. Okay, so it will be, so let's say the constant is called c. Then what I will get is e to the minus beta e of yw times e to the minus c, or e to the minus beta c, or e to the c, depending on whether beta is multiplied or not. And I get the same thing at the bottom, so it simplifies away. Okay, so there are several energy functions that are shifted by a constant which produce exactly the same distribution. It's both a bug and a feature, it turns out. Okay, so let's say I have a data point here. This is a training sample. I'm in one dimension here, so it's kind of a little confusing, but let's say that's a training sample. So what I'd like to change the shape of this energy function so that the probability of this guy goes up. And as a consequence, the probability of everything else will have to go down because it has to be normalized. So if I make the probability of something high, I have to make the probability of other things low, right? So in terms of energy, the result is that I'll have to make the, if I want to make the energy of one point low, as a consequence, to make this proper, I'll have to push up the energy of everything else as well. And you can convince yourself of this by doing the following calculation. So maximum likelihood consists in maximizing the likelihood that your model gives to the observed data by changing its parameter. Okay? So in other words, your model gives this probability to a particular point y. What you want to do is maximize the probability your model gives to all the points, or the product of the probabilities that your model gives to all the data points, right? Now, in fact, instead of maximizing the probability that your model gives to the point, you minimize the negative log probability that your model gives to all the points, okay? And the product turns into a sum of the data points. we talked about this formula last week in the case of supervised learning. So what you get is this loss function for a particular data point y. You get this loss function, which is the minus log of that minus the minus log of that, and I divide it by beta because it's more convenient this way. Okay, so minus log of that divided by beta is just the energy of the data point, and then you have 1 over beta minus log of that, and you get this. Okay, so this is the loss function you want to minimize, and minimizing this loss function will consist in making this energy as small as possible, pushing down on the energy of data points. This is what this will do. Okay, to minimize this loss, you make this small for a data point. So this is like pushing down on the blue spheres in the drawings I had before. And then you need to make this whole thing small, and the best way to make this whole thing small is to make all of those energies large as possible. Okay, because you have an exponential minus here, so if you want to make the whole integral here small, you have to make all those energies large. And this includes the energy of the current data point. Okay. So when you compute the gradient of this with respect to the parameters, you're going to get one term that's going to push down on the energy of the data point, and another term that's going to push up on the energies of everything else. Yes?
So in here we're going to specify the energy function, but let's say we use the energy function, we have to say PCA in there.
Uh-huh.
Would that be equivalent?
Yeah, actually, you could call this probabilistic PCA. In fact, there is such a thing as probabilistic PCA. I can't remember if it does exactly that, actually. But yeah, you could very well use a criterion like this on a parameterization of the energy that would be kind of like PCA. It would be a bit of a waste because, PCA, I mean, the advantage of it is that it might allow you to select the dimension of the space. So one thing it would allow you to do, for example, is to not specify the curvature of the distance to the point. So for example, imagine you do PCA, but in 3 dimensions, let's say, and the principal space is just a line in this 3-dimensional space. It could be that in certain directions, you want to pay more for moving in certain directions than other directions. Okay, so instead of using a Euclidean distance, you would use a weighted Euclidean distance, or what's called a Mahalanobis distance, which is, kind of a distance with kind of a metric, a matrix that determines the metric in a quadratic form. And using this kind of loss function will allow you to learn that metric as well. Okay, and in the end, what you would get is some sort of estimate of the density. If you take the exponential normalized, you get some sort of estimate of the density. Now you have to be careful though. You can't actually do this with PCA because this integral doesn't converge with PCA. Anything that has more than 0 dimension doesn't converge. The integral here doesn't converge. It's an infinite volume. So you have to regularize it. You have to say, okay, I'm only counting the volume within a restricted region so that my integrals don't blow up. Right? Okay, so you can sort of convince yourself of what's going on here by computing the gradient of the loss function with respect to the parameters. So here I just differentiate the loss function I had on the previous slide with respect to the parameters. So the first term is simply the gradient of the energy function with respect to the parameter at the data point. And the other term, again, I encourage you to derive this at home, which was to prove that when you have this loss function, you compute the gradient of this with respect to W, you get something that looks like this. Okay? So what you get here is you get a minus sign in front, and you get a sort of expectation under the model of the gradient of the energy with respect to the parameters. Okay? So this is, you can think of this whole thing here, let's imagine that y is a discrete variable. You can think of this as an average of the gradient for every value of y with respect to W. So you take every value of y, you compute the gradient for every value of y, and then you compute a a kind of a weighted average of this, where the weights are the probability that your model gives to each of those values of y. Okay, so what's the effect of this? Well, the effect is that the energy at a particular point will get pushed up because of the negative sign with a force that's proportional to the probability that your model gives to that value. Okay? So in particular, if your model gives probability very close to 1 to the data point, to the current data point, okay, then this energy will be very small already. This probability will be close to 1. All the other probabilities for all the other y's will be close to 0, and this difference will essentially be 0. Okay? So if the data point already has probability close to 1 under your model, there is no update that goes on. Okay? Your model is happy. It gives probability 1 to a data point you actually observe. Now in practice, that's never going to happen unless you have a single data point, because the probability has to be kind of spread around. So, whoops. So what happens is the points that are outside, that are different from y, get pushed up by a force that depends on how low their energy is or how high their probability is already. So if you have a data point and you have a point outside that has a low energy or a high probability, it gets pushed up very hard. Okay, the energy gets pushed up very hard, the probability gets pushed down very hard. Okay, so once you have this gradient, you do a step of, say, stochastic gradient descent. And that's the end of it. Okay, so the only problem with this is that this integral is very hard to compute. If y is a high-dimensional variable, like, say, the space of all images, you cannot compute this unless your energy function is very, very simple, like, say, a quadratic function of y, for example, which means it's a Gaussian, which means p is a Gaussian. Okay, so then you can compute Gaussian integrals and you can figure it out. But if E is anything that is worth actually using, then this integral is very likely to be intractable. Okay, there are ways to approximate those integrals. So for those of you who have taken courses on Monte Carlo methods, the Monte Carlo methods are designed to approximate quantities like this that are expectations of a particular function over a domain. Okay? And the idea is very simple. What you do is you draw a bunch of discrete samples from that distribution. Okay? So imagine you have a process by which you can draw samples from that distribution. You just draw a whole bunch of samples. For each of those samples, you compute the value of that function. Okay? So you draw a bunch of random y's. You compute the gradient of the energy at those random y's. Okay? And then you compute the average of those values. Okay? You don't have to weight them because they're already weighted by the sampling mechanism. Okay? Just the average basically is a good estimate of this integral. You replace an integral by a discrete sum where the points that you draw are drawn according to this distribution, and what you get is an estimate of the average. Okay? It's a classical thing of replacing an expectation by an empirical average. Okay, so they are called Monte Carlo methods. Again, those fall victim to curse of dimensionality. If Y is a high-dimensional space, you can sample all kinds of stuff. You're not going to need to cover any significant part of the space. Yes?
In Monte Carlo methods, in physics, there's a thing that is very hard to compute with full like integral, but derivatives of the log are feasible, right? So because when you're only handling relative changes, was there something similar?
Well, that's already a derivative of log if you can, right? We're actually computing the derivative of this with respect to W. That's what. That's what this is. No, okay. It could be interactive. I mean, you don't know how many samples you need to do a good approximation.
Monte Carlo are used
yeah.
for molecular simulations, which are also extremely high dimensional.
Yeah, that's right. Well, but they're not nearly as high dimensional as images, for example. The number of degrees of freedom in a, in a molecule is in the thousands, perhaps. Maybe in the hundreds. It's not in the million.
No.
Okay. It's hard, but. And there you have to do. Okay, one good thing is that you don't have to redo this for every data point, because this you have to do for every data point. But this is independent of data. It's just something that depends on the model, but doesn't depend on your data. Right. So you have to do it every time you change W. That's the problem. So every time you update W, you have to do it again. So there are other techniques. There are techniques called macro-chain Monte Carlo methods, MCMC methods. And those work pretty well if E is a continuous function or a differentiable function. Then you can use macro-chain Monte Carlo methods. Now, macro-chain Monte Carlo methods basically are akin to, imagine you have an energy landscape. You take a marble and you put the marble somewhere on this landscape, and you kick it with a random kick. It's going to move around. You run that simulation of this marble running around under gravity for a bit of time. And after a while, it's going to be at another point, and that's going to be a sample in your P of YW. And there are proofs that if you do this properly, the samples satisfy something called detailed balance, which guarantee that the samples you're drawing from this process actually are pretty close to the probability distribution you're looking for. And so you take a random sample, kick it, run the simulation down, and then you get a point. If the point is more likely to have lower energy than where you started from. It depends, of course, on the force of the kick. But I'm not going to go into the details of this, but there are various techniques like this. The one I just described is actually called hybrid Monte Carlo or Hamiltonian Monte Carlo. There are other methods that consist in just taking a point and then having a particular set of moves that you can do. And when a move makes you go down, you take it. So you select a random move, a random change of y to get to another point. And if the point makes you go down in energy, you pick it. If it makes you go up, you pick it with a certain probability. And if you run this for long enough, the distribution with which you observe the y's actually, the y's you observe distribute according to P of y given W. Yes?
The Monte Carlo process that we were talking about, what process is that using? Is it not using a Markov chain?
Yeah, Markov-chain Monte Carlo. So the Markov chain is the process by which you have certain moves, so transitions, if you want, from state to state. So you can think of this as a probabilistic transition matrix.
Yeah, the target
the target distribution is going to be the equilibrium distribution is going to be this distribution if the transition matrix has certain properties, so that the probability of going from a high energy state to a low energy state is 1. In other words, it's 1 over n if you have n possible such moves. The probability of going up, going up in energy is proportional to e to the minus the difference of the energies. Okay. Third method. It's very similar to this one, but it's kind of a, lazy bum version of version 2. Push down the energy of data points and push up on chosen locations around those data points or outside of those data points. And there's a whole bunch of methods that do this. One of the most famous one is called contrastive divergence. There's another one called ratio matching, noise contrastive estimation, minimum probability flow. I'm not going to talk about all of those. I'm just going to talk about contrastive divergence, because it's used in a model called restricted Boltzmann machines. So restricted Boltzmann machines is a model that was popularized by Geoffrey Hinton, University of Toronto. It turns out there was a similar model that was invented before that called harmonium back in the early 90s. But basically it's kind of a encoder type model. I'm not going to go into the details of RBMs just now, but I'm just going to explain what contrastive divergence is. So here's contrastive divergence. You pick a training sample, okay, and you push down the energy of that training sample, the usual thing. Okay, you don't push it just now. You wait a little bit. And what you're going to do is a macro-chain Monte Carlo process that's going to start from this data point and it's going to run down the energy surface, or perhaps run up because there is noise in this random process, in this macro-chain Monte Carlo process. So from the sample, move down in the energy surface with some noise, okay, with some probability of moving up. So one thing you can do if your energy function is continuous, you give it a kick, you run the marble down, you run the marble, and after a while the marble is going to be at some point. That's the point that you're going to pick to push up the energy of. If the white space is discrete, then you have some sort of way of moving from one point to another. And that process prefers to go downhill, but it might go uphill with some probability. Okay? And so anyway, so you start from a data point, you use one of those processes that preferentially goes down in the energy, then up, and then you take the point that you end up with and you push it up. Okay, so you push down the energy of the data point, push up the energy of the point you get at the end of this process. So it's very similar to maximum likelihood with Monte Carlo method, particularly a macro-chain Monte Carlo method, except that you don't run the macro-chain Monte Carlo for a long time. So the way people came up with this idea, basically Jeff Hinton came up with this idea, is by sitting in front of a Monte Carlo program that trained IBM and being tired of running this until equilibrium and kind of stopping it after a few iterations, essentially. I made that joke once in a talk where we were sitting, and he said, "Yeah, that's pretty accurate." So that's why I say it's the lazy bounds version of maximum likelihood. Not that Jeff Hinton is a lazy bound.
Do you have any guarantee that your goal is going to end up in another data point, or do you check for that?
Yeah, right. So it might very well end up in other data points. Yeah, that's true. And that's a problem. Yeah, that's true. So you have to rely on the noise. That's why you need noise. Okay. So I have to tell you that I have a profound distaste for those methods because of the sampling nature of it, and because sampling in high-dimensional spaces is not efficient. So it's good to know that those things exist, because there are situations where you can't really get away, without them. And there's a lot of interpretations of different algorithms that require this view of things. But in terms of kind of practical algorithms, I think there's major flaws of this approach because of efficiency issues. But you can get really, really cool demos with RBMs, and I very much encourage you to have a look at Jeff Hinton's website in Toronto, where he has cool demos of RBMs generating data, M-list digits and stuff like that. Huh? Hinton? Okay, so the name is Geoffrey, Geoffrey, and the last name is Hinton, Hinton, and he is a professor at University of Toronto, but he's also a researcher at Google. He's one of the big people in deep learning, and he was kind of hired by Google. Okay, so the result of this is that what this does is that it creates a groove in the energy function around data points, right? Because the data points are being pushed down, so they can create a groove in the energy surface, and the points around them are being pushed up because of this macro-chain Monte Carlo process that produces points that are getting pushed up. The things that are far away basically don't get touched because you never run the macro chain for long enough to get very far away from the data manifold. And so the shape of the energy function far away is undetermined. In a sense, you don't really care. You only care about the shape of the energy function around the samples for things that you are likely to observe. Okay, so there's another trick I should mention called persistent contrastive divergence, persistent CD. It's very similar, except that you don't start this microchain Monte Carlo run from a data point, but you have a certain number of particles that live in the space. Okay, so you throw a handful of marbles in the space, and you let them kind of, every time you want to update your parameters, you kind of let them run down the energy surface with some noise. Okay, so you kick them randomly, and you kind of have them run down the energy surface. And then at every learning iteration, you again push down on the energy of the data samples, but you push up on the energies of all those marbles, all those extra points. So what happens then is that those marbles tend to come into low energy points. But then if they go into low energy points, the energy of those points get pushed up because as the learning proceeds, it pushes up on the energy of points where those marbles end up. So after a while, it's going to roll out of it and go someplace else. Okay, right? So you get a hole. The hole gets filled up, and then after a while, it rolls out again, into another hole. This hole gets filled up. Okay, so it's kind of more efficient, if you want, than normal contrastive divergence in the sense that the marbles are used to really push up on things that you are likely to fall into. Yes.
The example of pushing the marble with the mass is same as proposal distribution.
Yeah, exactly. The question was, is it the same as proposal distribution? Yes. In the language of Monte Carlo methods. Let's take a break. A few minutes. All right, let's start again. All right, so let's talk about the next set of techniques. Number 4, and it's really I mentioned this one for the sake of completeness, or perhaps to kind of pique your interest, but it's kind of somewhat impractical, a little bit, for kind of complex models. So, but it's a cool idea. So again, we want to make the energy lower at the data point than everywhere else, and really we only care about the shape of this energy surface near the data manifold. We don't care about the shape far away. At least that's a hypothesis that seems reasonable. So one idea is to say, I'm going to try to make the gradient of the energy function at the data point as close to 0 as possible. I'm going to try to make the second derivatives at that data point as large as possible and positive. In other words, around the data point, I want the energy function to have 0 gradient, but at the same time, I want it to curl up. Okay, so that's going to create a local groove in the energy surface, right? That technique is called score matching. It was invented by a guy called Aapo Hyväläinen in Finland. Okay, so how do you measure the curvature? The curvature will be measured by the trace of the matrix of second derivatives of the energy function with respect to y. Okay, so for every direction in y, you have a curvature. Okay, so let's take a paraboloid, right? It's got, in 2 dimensions, it's got a curvature in this axis, and it's got another curvature in that axis, and those 2 curvatures might be different. Okay, the Hessian matrix tells you, the diagonal term will tell you the curvatures in those 2 axis dimensions, and the off-diagonal term will tell you how the principal axes of those kind of curvatures are oriented relative to the axes. That matrix is the matrix of partial second derivatives of the energy with respect to pairs of components of y. Okay, so you have a Hessian matrix Hij. It's a symmetric matrix, and the entry Hij is d2e over dyi dyj. Okay? So the diagonal terms are the second derivative with respect to each of the yi's. And the trace of it is just, the trace of the matrix is just the sum of those second derivatives, and it's an indication of how much curvature there is around the data point, right? Yes?
They don't use the determinant because it's an actual.
It's a little bit complicated to compute the determinant. Yeah.
But that could also be a saddle point. Because
It could be, well, so if it's a saddle point, some of those,
positive and the other could be negative.
right, so,
Total
yeah,
could still be positive.
okay, so the Hessian matrix could be non-positive definite. It could have negative eigenvalues, in which case you might have negative curvatures, yeah. But you'll see that in a trace.
You use the trace as an approximation to the determinant?
Well, you use it as something you can compute. You could try the determinant as well. It's just very unstable.
Factual.
Yeah. I mean, the determinant is actually a measure of volume, if you think about it. So it would probably be more appropriate. But then you have to think about how to do this, right? So to do the learning in a system like this, you have to take your energy function and you have to compute the derivative of the energy function at a particular point for a particular training sample with respect to the input, with respect to y, and then you have to compute the derivative of this with respect to the parameters. Okay, so what's the derivative of the gradient of the energy with respect to y with respect to w? Right? It's not that hard to compute, but it requires a couple of backprops in various directions. So you could think of the energy function as mapping y's to energies. Okay, so you can compute the gradient of this energy with respect to y by doing a backpropagation all the way to the input. So you backpropagate gradient all the way to the input, and what you have is the gradient of the energy with respect to y. Okay? Now you have to compute the derivative of this with respect to the parameters, because that's the way you need to adjust the parameters to make this vector shorter, because you want the derivative of the energy with respect to y to be as small as possible. Okay? So basically you have to do backprop in the backpropagation network to figure out how the gradient with respect to the input is affected by the weights. Okay? It requires a little bit of mind twist. Okay, but it's nothing compared to the other term. So the other term, again, is the trace of the Hessian. So you have to compute the gradient with respect to the parameters of the trace of the Hessian with respect to the input of the energy function. And basically, you can only do this if your model is very simple. If the energy is a very simple function of the parameters, essentially if it's a linear function of the parameters. Anything more than this, and it's just too hairy. I mean, you need to use kind of automatic differentiation, blah, blah, blah. It's complicated. So bottom line is, it's not entirely practical for a lot of models, and people don't tend to use this very much, but it's kind of a cool idea to think of. Okay, number 5 is a little hard to decode by just reading what's on the board here. Train a dynamical system so that the dynamics goes to the manifold. It's a technique there called denoising autoencoder that comes out of Pascal Vincent at the University of Montreal. And the idea there is very simple. Imagine, I'm going to use the board for that. So imagine again that we have data points. My computer is at risk because I drew 2 axes. Okay. All right. So these are my data points, my data manifold. It's missing some points. It's dropping points. Okay. You have to actually draw. So imagine we have a perfect energy function. So an energy function that takes low value on the data points and high values everywhere else. Now what I can compute is I can compute the gradient field of that energy function. So the gradient field, or the negative gradient field actually, is a bunch of arrows that point towards the manifold. So I'm probably going to have some sort of ridge here where arrows kind of start splitting. Oh wow, okay, it's dropping a bunch of things here. Oh, wrong color, yeah. So the arrows point towards the data manifold, if you can see that. And you could think of this as, so what I try to draw here is the gradient of an energy function, or the negative gradient of an energy function that points to, that takes small values on the manifold and high values everywhere else. Okay, so basically I'm a mountain hiker, and the data manifold is the valley, and I'm walking in a fog. And to go to the valley, I just look at which way it goes down, and that's where I walk. Okay. Now, one thing we could do. So what we need is some sort of box that tells us whether we are on the manifold or not, right? And we thought that this box should be something that computes an energy function. But in fact, it doesn't have to compute an energy function. It could actually do something much simpler than this, or much more complicated, depending on your point of view. So imagine you have an arrow here, and let's call this y, and let's call this y prime. Imagine that, I see. Okay, those things have to be in the right place. Now imagine that I have a box that when I give it a y, gives me a y prime that's actually the other end of the arrow. Okay? So I've trained this box somehow. So this box has some parameters in it. And I've trained this box so that whenever I give it the start of an arrow, it gives me the point of the arrow. Okay? Now if I take a y and I run it through this box multiple times, eventually the y is going to go to the manifold. And when I'm on the manifold, if this box is properly trained, if I give it a y that's on the manifold, I get the same y at the output. Okay? So that's a way of representing an energy function not by an actual energy function, but by the gradient field of that energy function. And the way I encode this gradient field is through a parameterized function that I train on data when I show it a data point. So the way you could imagine training this, and that's the idea of denoising autoencoder, is that you take a point on the manifold, you perturb it, okay, so you add noise to it and you modify it in some ways, or you do a Markov-Chain Monte Carlo of some kind, whatever. You get another point, and then you train a machine like this, think of it as a neural net, to produce the data point from the first point. Okay, so the input to the neural net is the point you just generated that's outside the manifold, and you train the machine to produce the data point that you originally picked. Okay, so in fact, it's kind of a restricted version of this where all the arrows actually end up on the manifold. So it's not quite like what I drew here. Okay. So a particular instance of this is the so-called denoising autoencoder. And essentially, it's exactly what I just described. So you take a data point y. Oh, nice. Yeah, I see. Here you go. You take a data point y. You pass it through a noise function. Okay, and you train the machine to produce y. Okay, so y is a point on the manifold, and the noise function is going to generate another point, and you train the machine given the noisified y to produce the y on the manifold. That's the so-called denoising autoencoder. Yes?
vectors. So if I think of it as a narrow valley, denoising is going to make the valley broader.
Well, not necessarily. There's no real notion of kind of this steepness of the valley here.
It's going to make the denoise version of that energy to be same. So it's going to make the
No, it doesn't make the energy to be the same. There is no energy function here, right? There's a gradient field, and if you could integrate that gradient field, it would give you a potential function which is like an energy. Okay, so imagine that I give you a vector field. If I know the value of the function on the data point, for example 0, okay, by integrating along a path, I can figure out the value of the energy function by just integrating over a path. And if this vector field happens to be the gradient of some energy function, then I can reconstruct this energy function this way. Okay, but I don't actually ever need to do this. I don't ever need the energy function. I just need to be able to go to the manifold from another point. So in essence, this model is sufficient. Okay, I could have some fake version of the energy that would be the energy would be essentially the square distance between n of y and y, between the input and whatever is produced by the system. The length of the arrow, if you want, could be the energy function. Okay. Now observe that there is a slight issue here. You can't really think of this vector field as the gradient of an energy function, because it could very well be that the curl of that vector field, if you know what that is non-zero. So in other words, I could have, by some bad luck, I could end up with a vector field with vectors that are kind of like this, right? And then I can't integrate this vector field to produce an energy function. This is not the gradient of an energy function of a potential function, if you want, because the function has to grow as I go around the loop, and it has to kind of be the same value all the time. So vector fields that have loops like this are called vector fields with non-zero curl, and if the vector field has a non-zero curl, then you can't really express it as the gradient of an energy function. We can still define an energy function as the square difference, for example, between the input you give to the system, so a particular point here, and the output. That would be the energy of that input vector. So the length of the arrow at any point you could think of as some sort of energy function. It's kind of a bad energy function, but you could think of it this way. Yes?
So don't you also here face kind of sampling problem, because you have to generate all points with,
Right. Yeah, so it's the same problem. You have the same problem with this as you have with things like contrastive divergence, which is that you need to sample the noise around each data point, with enough points that you cover the space of possible things. And in high-dimensional space, you might have a hard time really covering all the directions. It's quite possible. But in practice, it actually works okay, surprisingly. Okay. All right, so this is, in my opinion, the most interesting one. This is the kind of stuff that actually a lot of research in my lab has been focused on for the last several years. Not quite 10 years, but more than 5. And it's essentially using a regularizer that limits the volume of space that can take low energy. So imagine a parameterized function, a parameterized energy function that's designed in such a way that it has a regularizing term in it, that tries to push down on the volume of stuff that can take low energy, that takes low energy. So the larger the amount of space that has low energy, the higher the regularizer. So minimizing the regularizer, we kind of shrink wrap the data in a kind of low energy volume. And there's kind of various techniques to do this. The most popular one is something called sparse coding. Okay, so you're going to have lots of lectures on sparse coding, so I'm just going to introduce the basic idea. And you'll have guest lectures and things like this on kind of the more mathematical aspects of it, because there's lots of work on kind of the applied math side of sparse coding, which I'm actually not a particular expert at, and there are people in my lab who are much better than me at this, so I'll try to twist their arm so they can give you a guest lecture on this. But this is what sparse coding does. It tries to approximate the data manifold as a union of low-dimensional linear subspaces. Okay? There's a particular technique to do this called KSVD. There are other techniques also, but it kind of looks like this a little bit. So here, the energy function, you have a bunch of lines. So you have a line here, you have a line here, you have a line like this. And each of those has kind of a quadratic PCA-like energy function attached to it. And the overall energy function is the sum of all of those. So you get a groove around the data because there's lots of planes that intersect there. But you get those kind of artifacts here. So this works really well when data is essentially a union of low-dimensional planes, right? Because that's what this is. So for example, multiple planes like this, data that's kind of multiple planes. Do you guys know what this, there's this kind of funny type of stone that you find in the desert called a sand rose. I don't know, actually I don't quite know what the name in English is. It's called rose de sable in French, but it's this thing it looks like lots of planes that are intersecting each other. That's the kind of distribution something like this would model very well. Okay, so here's the basic idea behind sparse coding or sparse modeling. You have an input vector y. So basically, I've represented here what could amount to a graphical model, a factor graph in particular. So a factor graph has variable nodes, the bubbles, and has factors. They're called factors because people generally think in terms of probabilities, but in fact they are kind of additive. So they're factors in exponential space, but they are additive in the energy space, if you want. So anything that's in a red box is a factor. And you can think of it as a term in an energy function, additive term in an energy function. So this energy function has two terms. One that says, I'm going to take the what's called a feature vector, okay, that represents the input. I'm going to run it through a decoding function, and then I'm going to measure the reconstruction error between the reconstruction produced by running z through the decoding function and the original data point y. Okay, so this square box distance here, that's a factor. Okay? And then the other factor here is going to measure some information content about z. In particular, in sparse coding, this would measure the L1 norm of z, which is kind of a convex relaxation of how many terms of z are non-zero. You could think of it this way. So here it is. That's the energy function. So you will notice that this energy function is actually not quite an energy function because it's not an energy function of just y and w. It's an energy function of y and z. There's also the w parameter, which I didn't write, where z is this latent variable. The real energy function is the minimum of this over z. Okay? So here we have two terms. The first one is the reconstruction error. And we're going to make this decoding function just a linear operation, okay? So here we take the z vector, we multiply it by what's called a dictionary matrix, hence the D. WD stands for dictionary matrix. And then we measure the square reconstruction error, which is this term, that's the first factor. And then the second factor is the L1 norm of zj multiplied by some parameter lambda. Okay, and it's that. So you compute so each of these blocks here with an arrow pointing is a deterministic function. Those guys are variables, and those guys are factors in the energy, additive terms in the energy. So this guy here, you take the absolute value of each of the components, and the factor just computes the sum and multiplied by a coefficient lambda. Okay, so let's assume that WD is known, okay? Someone gave you WD. Now, to actually measure the energy of Y, I have to compute the minimum of this with respect to Z. So I have to compute the Z that minimizes this energy. And the result is a Z vector, a Z hat vector is the one that minimizes the energy. And this minimum energy is actually the energy of Y, okay? So it's kind of like K-means. K-means had something like this, if you remember. In fact, this is very, very similar to K-means in many ways. Where is K-means? Here's K-means. So K-means here, the energy of Y is the minimum over Z of Y minus WI ZI for sum over I, where you can think of this as the product of a matrix W, very similar to the WD we have here, times a vector here, which happens to be a 1 of n code, okay? So here, for K-means, the energy of K-means is the minimum of the square reconstruction error under the constraint that the Z vector has to be a 1 of n code. It's only allowed to have a single 1 moving around, and all the other components are 0. With sparse coding, we're allowing more than one component of Z to be non-zero, but with the L1 norm, we're actually giving a penalty to the system for making too many of them non-zero. It's the result of this L1 penalty. It's going to want to make many components of Z 0. The ones that are non-zero can take whatever value they want. Okay, so now think about this geometrically a little bit. So imagine that we know which subset of Z should be non-zero to make this overall thing small. Okay, so we know exactly which components of Z should be non-zero. And finding the optimal values of the Z that do the best reconstruction is a very simple least square problem that can be done by solving a linear system. Okay? The complexity of this minimization here is not to find the precise values of the Z component, but is to find the subset of Z's that need to be non-zero to produce the best result. Okay? It's called the active set. Okay, so a couple more things about this. So again, there's going to be an inference algorithm, which means give me a Y, I give you the optimal Z, and I give you also the resulting energy. But then there is a learning algorithm, and the learning algorithm for this consists in finding the WD that minimizes the average energy over a training set. Okay? And by energy, I mean the energy after minimization with respect to Z. So the algorithm goes like this, and I should have a slide for this, I'm not sure why I don't have it. The learning algorithm goes like this. You take a point Y, so you have some starting value for WD, okay? You take a point Y, you find a Z that minimizes this L1, L2 energy for this particular Y, okay? And now you compute the gradient of the energy with respect to WD. It's very simple because it's basically just a squared error. Okay? So the gradient of this with respect to WD is going to be yi minus Z times Z. Okay? That's actually minus the gradient. So you update WD with yi minus Z times Z. Okay? It's an outer product, I should say. So y minus Z is a vector times Z transpose. It's an outer product. It's Z transpose. It's just least square, okay, with stochastic gradient descent. Now there's a slight problem with this, which is that if you're not careful, what's going to happen is that the WDs are going to grow extremely large, so that the z's could get correspondingly small, so that the second term could be small. Okay, so there's a indeterminacy in this problem, which causes a divergence of WD. WD is going to grow extremely large, so that z can become small. So to prevent this from happening, you have to normalize the columns of WD. You have to make sure that the columns of WD are within norm 1, so they never go above norm 1 or some fixed norm. Doesn't matter if it's 1 or not. Okay? So the columns of WD can go above a certain threshold, which means Z cannot go below a certain threshold if you want an appropriate reconstruction for Y, and that solves the problem. Okay, now another intuition for how this works. In the end, Yi is going to be reconstructed as the product of WD times Z, but Z is going to have a small number of non-zero components. And what that means is that Y is going to be reconstructed as a linear combination of a small number of columns of WD. Okay? So when you train the system, the columns of WD will end up being basis functions, if you want, basis vectors, so that with a small number of them that you linearly combine, you can reconstruct anything. Generally, the WD matrix has more columns than it has rows. In other words, the basis is overcomplete. So you have more things that you can linearly combine together to reconstruct an input. Then you have dimensions in the input. But then because a subset of them are being selected, things are fine. So as it turns out, this penalty term here, the L1 penalty term, has the effect of limiting the volume of stuff that can be exactly reconstructed, or reconstructed with low energy. And I'll come to this in a minute. I have some intuitive explanation for that. So let's say we have points in our input space and points in our feature space. So this is the space of Y's at the left, and this is the space of Z's. And let's say we have a training set. The dark blue points here are training samples. Okay, so they are kind of a manifold, if you want, in our input space. Okay, so if I have enough space in the feature space, enough possible configurations in my feature space, and I train my system to reconstruct input points properly, it's got enough different points here, different configurations in the feature space to be able to reconstruct any point in input. Okay, so what I can do is use my training points, train a reconstruction engine function, so that any of those points can be reconstructed with low energy. Okay, and if I'm not careful, the system will be able to reconstruct any point in my space. Okay, so for example, let's imagine that I use the sparse coding energy function here, but I don't put a sparsity constraint. I remove that term. I set lambda to 0. Then I ask the question, what value should WD take so that I reconstruct my input points exactly? And it doesn't matter. WD could be any random matrix as long as it's non-degenerate, as long as it has as many independent columns as it has rows. Then any Y can be reconstructed as the product of that matrix by some vector Z. I was only find a vector Z that exactly reconstruct any Y if WD is full rank. As rank the same dimension as the input, okay? So obviously that's not interesting. I get perfect reconstruction for everything. And so what I get now is an energy function that's flat. It's 0 everywhere, regardless of whether a point is a training point or not. I get a flat energy function. It's bad. The sparsity constraint says, okay, you're not allowed to reconstruct everything. You pay a price for reconstructing a large part of the input space. I'm putting a constraint so that the number of components of Z that are allowed to be non-zero at any one time is relatively small, so that you can only reconstruct the subspace. So basically you're constrained to kind of a PCA for those points, and another PCA for other points. Okay? So the result, what we're doing with this Okay, so this is the bad example where the feature space has enough configurations that any point on the input can be reconstructed exactly, and that will lead to trivial solutions that are not interesting. But what if I constrain the feature space to only have as many configurations as I have data points on my manifold, namely 3 here? Okay, so k-means does that, for example. You only have k points that can be exactly reconstructed. If you have k quadratic balls, you have k minima to the energy. At the bottom of those balls, the energy is 0, but everywhere else is non-zero. So you only have, k different configurations, k different points in the input space that are exactly reconstructed. Everything else is not exactly reconstructed. So here I'm trying to place ourselves in a kind of slightly more general case where what I say is that I'm putting some constraint on the feature space in such a way that the number of possible configurations or the volume of possible configurations is limited by a regularization term. So now imagine I only have 3 points in my feature space. I have 3 points in my training set. So if I've trained my decoder function in such a way that these points reconstruct the training points, okay, when I get another point, it's going to have to go to one of those 3 points. So if I start from another data point that's not in my training set, like this noisy image here, it only has those 3 points to where to go. It can't go to any other place, okay? It's going to choose one of those 3 points. So it's going to go to maybe this one that happens to be the closest. And then when I reconstruct, I'm going to reconstruct the original data sample that I used to train this point. And so I'm going to get this cleaned up version of this pepper here. Okay? So that's the general principle of put a regularization term in your energy function that causes the volume of stuff that is exactly reconstructed to be small. And that will automatically make the energy of stuff outside your manifold of high data density high. All right? And sparse coding is the best example of that. Yes?
How is the dimension of C compared to the dimension of X?
So, of Y, you mean?
Yeah.
Generally, it's larger. So Z is generally higher dimension. I mean, that's what I said by saying WD has more columns as it has rows. So another way of saying Z is larger than Y in dimension. Okay?
How do you choose regularization?
How do you choose lambda? Very carefully. Well, basically, it depends what you want to do with Z. Okay, so if you want to do image denoising, there are ways to do this. If you try a few value and you see which one works best using an evaluation, some kind like that. Very often people use this for feature extraction. So this kind of method, sparse coding, has been very popular to do mid-level feature extraction for computer vision systems. All of this has been a little bit displaced by convolutional nets, but there was a period of a few years where all the mid-level features for kind of traditional computer vision object recognition systems were basically obtained using sparse coding. And it's pretty good, unsupervised technique for learning features. If you don't worry too much about computational cost. Although there are techniques to make this inference very fast, it's still expensive. So right. So an example for this. So here's how you would use this. You would so say that you want to use this for MNIST, handwritten digits. So you take the set of handwritten digits and you train WD so that the digits are properly reconstructed using sparse representation Z. So Z would be typically something like 1,000 or 2,000, 4,000 dimensions. Okay? Now for every digit, you can compute the optimal sparse Z that reconstructs a digit, and you can use this as a feature vector that you feed to a linear classifier. And you can train a linear classifier to using that feature vector. And that works okay. Works pretty well. You're referring to k-means or soft k-means as a way of doing this. This generally works better than k-means. There's a slight problem with sparse coding, which is that it's unstable in the sense that a small change in Y can produce a very large change in Z. And for recognition, it's not always a good idea. If the transition from, that if a change in Y that produces a large change in Z is at the boundary of two categories, it's fine. But if it's inside of a category, it's probably not good. Let's see. I wanted to show you some pictures of this kind of stuff in action. Oh, here we go. Okay, so here are example for MNIST. This is the basis functions. In fact, I believe these are for an encoder matrix, but they're exactly the same for a decoder, pretty much exactly the same for a decoder matrix. So these are a representation of the columns of WD when you train a sparse coding system on the MNIST dataset. Okay, so you take all the digit images from the MNIST dataset, and you train a sparse coding system with, in this case, I think probably a couple hundred. I can't count how many. Maybe 400. Can't remember exactly how many of those there are. And so each column of WD is going to be a vector of the same size as the whole MNIST image. MNIST image is 28 by 28 pixels, 784 pixels. So each of those guys is a column of WD represented as an image of the same size as the input vectors. Okay, and what you notice is that what the system learns is that those basis functions essentially are little pieces of stroke. And the reason for this is that now you can reconstruct any digit as a linear combination of a small number of these guys. Okay? So if you think about what are the elementary parts of digits from which you can take a small number of those parts and reconstruct any digit from a small number of those parts, they end up being small pieces of stroke, right? Small strokes. And the system learns this spontaneously. Right? So if you assemble this with that and that, you get a 7. And, those various pieces, by assembling them with each other, produce essentially any digit you want. So this is unfortunately a slightly different algorithm here, but the result is qualitatively the same. So this is a learning algorithm running, the sparse coding learning algorithm running on, again, these are, each little square here is a column of WD, so an elementary basis vector. And this is trained on natural image patches, grayscale images. Okay, so you take random patches from grayscale pictures, hundreds of thousands of them, and then you train this algorithm on this. You start from a random initial configuration, and as the learning proceeds, you start getting those little oriented edge detector. In the end, you get something like this. Okay, so the system learns that images are basically a linear combination of a small number of edges. Okay? Now, it turns out, so there is a reference for this that I showed on one of the previous slides. O'Southern and Field, 1997. So they came up with the algorithm to learn WD. And those guys actually are neuroscientists. They're not mathematicians, they're not computer scientists, they're not machine learning people. They're neuroscientists, theoretical neuroscientists, or computational neuroscientists, actually they're called. And the reason they came up with this thing is that in the end, so this is a very famous paper, when you look at the receptive fields of neurons in the brain in V1, the primary visual cortex area, you get filters. So the pattern of synaptic weights of neurons, or what it looks like they're doing in the visual field, look very much like these. Now, if you remember when we talked about convolutional nets, I showed you some pictures of filters that the network ends up learning from natural images when you train it to recognize objects. And they look very much like that too. Many of them look very much like this, right? I don't know if you remember that. Now, there's something weird about those, which is that they're not really filters. They are reconstruction basis functions. They go backwards. So they're not like, if I go back to this diagram, they're columns of this matrix. So it's not like you take an input and then you compute the dot product of the input with a bunch of filters and you get the result. It's the other way around. You have some feature vector, you multiply it by this, and you kind of find a feature vector that will reconstruct the input. And it's kind of hard to see how neurons could do this, minimize this L1, L2 function. And so, to some extent, you can think of this model as going backwards. Like modeling feedback connections in the brain, not feed-forward connections. And the next stuff we'll talk about is to actually kind of reunify those things. So there are models that go both ways. They're called autoencoders. In the case where there's a sparsity constraint on the hidden layer, they're called sparse autoencoders. So these are neural nets in some ways, where you take an input vector, you run it through an encoder, you get some vector, and then you run this vector through a decoder and get a reconstruction error. And you train both the encoder and the decoder to minimize the reconstruction error while imposing a sparsity constraint on the hidden layer. Okay? So in the end, what you get is a two-layer neural net. You can look what you're doing here. Okay, so you start with a vector, you run it through an encoder function, which itself could be a multi-layer neural net. So it could have linear modules and maybe ReLUs and linear modules and ReLUs and whatever. And then there is a decoder. Generally, it's just a linear module. So this would be WE, WD for decoder, also for dictionary. Yeah, those things don't flow very well. And then the cost function would be a squared error between whatever comes out of this, which I'm going to call W tilde, and the original W. So it's just a neural net, essentially, but it's a funny kind of neural net where the input and the desired output are identical. Okay, so when you train this neural net, you train it so that you feed it an input and you tell it your output should be equal to your input. Okay, your neural net should actually compute the identity function. How hard could that be? But there is a twist, and the twist is that this should be sparse. The state, the hidden state here, Z, should be sparse. And then that makes the problem complicated, and it makes it interesting, and it makes the system learn appropriate representations of the input through the Z, and it's very much like sparse coding. Except that now you have an encoding function to compute the Z, which could be very fast. So you don't need to solve the minimization problem anymore. This is called an autoencoder because it learns the identity function, right? Because the output is equal to the desired output is equal to the input. That's the definition of an autoencoder. Okay, any questions? Yes.
Typical use cases with Z still have a higher dimension than the Y?
Yeah. Okay, so there was a traditional way of building autoencoders, which was they're called bottleneck networks, where the Z would be kind of smaller dimension than Y. You could think of it as kind of a compact code that represents Y. And if the encoder or the decoder or both are nonlinear, then it's more powerful than PCA in a way. But it turns out experimentally, so when in the first days of backprop, back in the 80s, people like Jeff Hinton and me and other people thought this would be really cool because you could have nonlinear PCA and you could extract compact codes for data and that would be wonderful. It turns out not to work. It's very difficult to train those networks with narrow bottleneck.
With something like PCA, right?
Right, so if you just have a two-layer network, then it just does PCA. If you have nonlinearity, then it becomes very difficult to train, and in fact, it doesn't do anything because it's too hard. And what happened over the last 10 years is that people realized, wait, I don't actually want a compact code. I want an expanded code because I want to be able to feed that to a classifier so that it does a better job. So I actually want the middle code to be higher dimension than the input. So it's high dimensional sparse, and I can discriminate things. The problem, of course, is that if you just train an autoencoder with a wide hidden layer, then it's going to learn the identity function just like that, and the energy function, basically the reconstruction energy, will be flat 0 for every Y. And so putting the sparsity constraint on the Z is what allows it to have low reconstruction error on the data, but high reconstruction error on everything else because of the limited capacity of the hidden layer. Because of the principle I just explained, where you can limit the number of different configurations of the hidden layer of the code. Yes?
I want to think about it as having the similar function as kernels.
Kernels, well, it's not...
Like you map it into a higher dimensional space.
Yeah, that's right. So kernels do this. They do it in a different way because, you have to use a kernel function that you apply that is symmetric. That takes two arguments. One of the arguments is the input vector. The other one is training sample. So here you don't have that idea. But it's the same idea that you want to expand the dimension of the space so that things are more discriminable. Yeah, I mean that's one of the things I talked about also when I talked about convolutional nets and what are proper features and stuff like that. Yes.
So these sparse encodings are supposed to be binary?
No.
No. Why not?
Well, they can if you want, but there's no constraint for them to be binary.
You think about it as like an actual code you would send through a wire, right?
Oh, I see. A code in terms of like a binary code. No, it makes life difficult if you insist that those codes be binary. I mean, so RBNs are like that. Restricted Wilson machines, the hidden layer, you could think of them as funny kinds of autoencoders, where you have, and I come back to that, where the two matrices, the encoding and decoding matrices are transposes of each other. And the reconstruction error is not a squared reconstruction error, but it's a dot product. It's a negative dot product. And where there is a constraint that the hidden layer and even the visible layers are binary. But it's, anytime you have something that's binary, it's complicated to backpropagate gradient to it and all that stuff. So which is why RBNs are not trained with backprop, they're trained with contrastive divergence. Yeah, any other question? Okay. Thank you.